Okay, Chapter 9 worksheet. So a couple of symbols that we need to make sure we know for the test and for this. The probability of making a type 1 error is going to be alpha. Symbol represents the type 2 error. This is the beta. Now these are the probabilities of making them, so they're going to be percents. Our alternative hypothesis will either be H1 or HA. They're kind of used interchangeably in the notes, and they're fine interchangeably. What formula represents the null hypothesis is always that H with a 0. So 0 is sometimes called null in different languages. The significance level is also alpha. Okay, researchers are determining whether to study the age of a victim is a factor in reported scams. The researchers are tested to see if half of all reported victims in the elderly victimize the elderly. They randomly sample 350 reported scams over the past 10 years from the Better Business Bureaus and note that for 287 of them, the victim is over 65 years old. So, things that we know. We'll do these. So, alpha is going to be our significance level. So, if our significance level is not given, it is assumed to be 0.05. Now, if we look in here, we'll realize that this is a proportion. And the reason I know it's a proportion is the question that they're, one, I don't have a mean, so that's kind of a tip off. The other is they're asking them a yes or no question. Have you been a victim of a scam? They're getting people that are victims of a scam, and the question is, are you 65 or older? So it's a yes or no question, which makes it binomial. The trick is they didn't give me the p hat, technically. They gave me a way to find it. So the way I find it is this sort of the proportion of yes answers or successes in my sample. So in our sample, we realize that 287 over 350 is our proportion. And so we'll take that. So 287 divided by 250. 287 divided by 350. Makes more sense. Is 0.82. So our p hat is this 820. If it's just 82, you can leave it. If it goes off into lots of decimals and you're having to round, it's almost better to use the fraction as p hat. So then the question is p. So p is what our hypothesis is testing. So what is the question that we're asking? So the researchers are testing, there's our keyword, to see if more than half of reported scams victimize the elderly. So that means our P is, we're asking if that is greater than half or 50%. So that's why our P value is going to be E. N is our sample size, which is 350. And X is going to be the number of samples that, or the number that said yes, so that's going to be our B. When are p-values negative? So the P in p-value means probability. And rules with probability is my number has to be between 0 and 1, which means it can never be negative. So our answer is going to be this E. P-values are a probability, and probability is never negative. Test statistics can be negative, but test statistics are related to our z-values, and we know our z-values can be negative or positive. As the degrees of freedom in the t-distribution increases, the distribution approaches. So as the t-values are we're dealing with that table because we don't know the standard deviation and we don't know the mean. So there's two unknowns, so we have to use a t-table. So what we're using on that is we're trying to get to a normal distribution. So as we get more degrees, or in other words, as our sample size gets bigger, we start to get closer and closer to that normal distribution. Okay, so an example of one. A survey was conducted to get an estimate of the proportion. So that tells me that I'm going to be using a P in this hypothesis testing among graduate students. The report says 38% of them are smokers. Chatterley doubts this result and thinks that the actual proportion is much less than this. So his guess is he wants to test if that point is less than 0.38. So if I'm less than 3.8, then I'm either bigger or equal to I say 8 and then I write 5. 8. So if on a hypothesis testing, you could either write, I always just, if I'm doing less than to me the opposite is greater than or equal to. We accept both in the notes and on the test. These two things mean, oh, I keep doing that. These are both correct. So if you write them one way or the other. Now the question is, which is null and which is alternative? So the null always includes the equals, and the alternative is the other one that doesn't include the equals. Hence our answer is C. You need to draw a distribution that represents the rejection regions. So when we're making rejection regions, we're going to use critical values. These are our walls. So anything in the middle is I fail to reject. Okay. Our rejection regions is from that critical value or that wall towards the tail. So I can have a critical value here towards the tail. Okay, so the critical value is always the value I use to define my rejection region. The critical values are always found from our tables, our Z table at the very, very bottom, or on our T table. A sample data is converted to Z or T for making a hypothesis test. So we have our critical value, so we have our border. We then use a test statistic to represent how our data relates to that set parameter. In a hypothesis test, the probability of getting a sample statistic as extreme or more extreme than, so here's our key word here in this one, probability. So probability means that it is my p-value. David wants to complete a hypothesis test with the lowest possible probability of error. If he sets the significance level 2.01 and his sample is truly random, what has he predicted to be more severe? So he's made this area very, very small. You notice that when we do it, our default is 0.05. Like the biggest we want to get is like maybe 0.10. You won't see a lot higher than 0.10, not especially in the stuff that we're doing. So what does this represent? This significance level is going to tell me the area of the rejection region. So the bigger the area, the more room I have to fall into it and reject it. So if you remember our table, reject is first and fail is second. So type 1 is I rejected it when I shouldn't have, and type 2 is I failed to reject when I shouldn't have. So if I'm making this area really small, I do not want to reject it, right? I want it to be less likely for me to reject it. So that's going to be a type 1 error. Why do we use infer statistics? So it's to make informed predictions about parameters using data from samples. So I use my sample to make a guess about our parameters, typically mu or proportion. And it's inferential because we're inferring an answer about a big population from our samples. Parameters and statistics describe the population, so parameter, population, and the sample statistics respectively. Explain why the phrase 95%, what it means. So power is I reject the null hypothesis when it's true. So this is I reject and I was right. So I have a 95% probability of rejecting the null when the hypothesis is true. So I rejected the null. The alternative is true because if I reject the null, then I take. So I rejected the null. The alternative was true. So I was right. Explain what the member of 5% significance level means. So again, remember we're going on this. These ones are probability. 5% significance means I have, so if I have 95% power, I had 95% of rejecting the null. When the alternative true, so this is, I have the probability of rejecting the null when the null is true. So this is a problem because I rejected the null. I said reject HO. In reality, HO was true. So I should have failed to reject it. It was right. I want this to be wrong because this is a type 1 error. It's a type 1 because it is stemming from rejecting the null hypothesis. When should we proceed with caution? So when I say proceed with caution, it means my assumptions have mostly been met, but I might not be super happy with them. So when should we proceed with caution? When the assumptions have not been met, so the probability of making an error could be higher. That's what I want. So if either they have been not met or like barely met. So like say I had something that was skewed and I had a sample size of 31. I'm going to tell someone to proceed with caution. Or I'm skewed and I have a 29. I'm still going to proceed with caution. So I may run the numbers, but I'm not going to be super confident in my findings because I don't have enough data. A certain brand of jelly beans are made so each package contains about the same number of beans. Filling is not perfect. The packages are filled with an average of 375. Okay, so I've got that average of, so that is going to be my mean. But the number going to each bag is normally distributed with a standard deviation of 8. Yesterday, Jane went to the store and purchased 4 of these packages in preparation for a spring fling. She was curious, so she counted the amount of jelly beans in these packages. Her 4 bags contained an average of, so my X bar equaled 382. So which statement is correct? 382 is not a parameter. He's my X bar, which means he's a statistic. X is not right. So both of these numbers here are coming from my population. My 382 is coming from my sample. So 375 is my population parameter. Suppose our p-value is 0.044. What will our compute be on alpha? So at 0.1, so we compare our null, our p-value, 0.44, to our p-value. Well, my p-value is low, so we reject. My p is low, the null must go. So what happens if it's 0.05? Well, 0.44 is still smaller than that, so I reject. What about 0.01? Well, now my null is higher, so I failed to reject. So that's where that B1 comes in. Classify symbols as parameters, statistics, or neither. So our parameters from this group, parameters are going to be mu, sigma, and then p. My statistics is going to be X bar and p hat. And then neither is the X and the alpha. Only parameters are allowed to go into a hypothesis statement. You will never see a hypothesis statement with an X bar.